All right, let's just jump right in. We've all seen the videos, we've read the headlines about self-driving cars. But underneath all that excitement is one of the toughest engineering problems maybe ever. How do you prove that an autonomous vehicle is safe? I mean, really prove it. It's more than just a technical question. It's almost philosophical.
And yeah, this is really the heart of it all. Just think about it. The real world is, well, it's chaos. A kid chasing a ball into the street, a sudden downpour that cuts visibility to zero, a deer on a foggy night, another driver just doing something totally bonkers. The number of things that can go wrong is basically infinite. So how on earth do you test for infinity?
To even start answering that, we have to talk about a huge shift in how engineers think about safety. For a long, long time, car safety was all about what's called functional safety. Basically, asking the question, is the system broken? Fixing bugs, making sure a sensor doesn't fail. But with AI, that's just not enough. So now there's a new idea called SOTIF, that's safety of the intended functionality. And this asks a much, much harder question. Even if the car is working perfectly, is the design itself actually smart enough to handle the complete craziness of the real world?
So you might be thinking, okay, if we need to test the design against the real world, let's just drive. A lot, right? Well, that leads us straight into our first massive wall, what the industry calls the billion-mile problem. Turns out you literally can't just drive your way to safety.
The numbers here are they're staggering. To statistically prove that a self-driving car is even a little bit safer than a human, you'd have to drive it for hundreds of millions, maybe even billions of miles. That would take decades. It would cost an absolute fortune. It's not possible. The old way of doing things is completely broken.
And this is really where that SOT of philosophy shines. I want you to think of it like an old explorer's map of the world. The goal is to shrink the parts of the map labeled unknown, unsafe. The here be dragons territory of weird situations we haven't even thought of yet. And at the same time, we want to expand the known safe part of the map by finding those dragons and proving the system can handle them. So if we can't explore that map by physically driving, how do we do it? We do it by building new realities, digital ones. We recreate the world inside a computer, where we can drive millions of miles in just a few hours. But you can't just hit a button and hope for the best. You need a really structured way to turn those abstract fears into concrete, digital tests that you can actually run.
And this is how they do it. It's a process called the scenario funnel, and it's actually pretty clever. You start at the top with a super simple idea, an abstract scenario, something like a car changes lanes on a rainy day. Then you narrow it down to a logical scenario by adding rules, like the car speed is somewhere between 80 and 100 kilometers per hour. And finally, for every single simulation, you create a concrete scenario where you pick exact numbers. The speed is precisely 95.5. This whole process turns a fuzzy idea into a repeatable scientific experiment.
So, great. We have our digital world, we have a way to make tests, we're done, right? Well, not quite. This brings us to the next big challenge. Hunting for rare dangers. Because even in simulation, it turns out we're still looking for a needle in a digital haystack. And here's the thing you have to remember. Accidents are, by their very nature, rare. Think about it. Most of the driving you do is totally boring and nothing happens. So if you just run random simulations, guess what you're simulating? Billions of miles of boring, uneventful driving. You could let your computers run for years and still completely miss that 1 in a million situation that causes a disaster.
This is where the real genius comes in. It's a statistical trick called importance sampling. The idea is actually brilliantly simple. If you're looking for needles, why waste time searching the whole haystack? Just go to the parts where you think the needles probably are. In our world, that means we stop testing everything randomly, and instead we focus all our computing power on the most high-risk, dangerous, scary scenarios we can dream up.
This visual explains it perfectly. Think of this graph as all the possible things that can happen. The big, wide area with light sampling, that's all the normal, safe driving. We pretty much ignore that. Instead, we do heavy sampling, way over on the right, in the risky zone, the scenarios where a car slams on its brakes right in front of you. We are deliberately trying to make the system fail over and over again, so we can find its weaknesses fast.
But hold on a second. If we're only testing the dangerous stuff, aren't we just cheating? Aren't we cooking the books? How can you possibly get a real, statistically valid result about the car's safety in the real world? This is where a little bit of beautiful math saves the day.
Okay, don't let the symbols here scare you. You do not need to be a math whiz. All you need to know is what this equation does. This is the engine that makes importance sampling work.
It takes all the results from our crazy, high-risk tests and it averages them together in a very special way that gives us the final, true probability of that bad thing happening in the real world.
And this little piece of the puzzle right here is the secret sauce. For every single bias test we run, this formula calculates a weight, or a correction factor. It basically keeps track of how much we cheated by making the scenario more dangerous. Then, by applying that weight, it cancels out our bias, making sure the final answer is a totally accurate reflection of reality. It is an incredibly smart solution.
So that leads us to our next big topic, the universal rulebook. Because having this powerful testing method is great, but it's not very useful if the entire global auto industry can't work together. If every company uses its own special tools, you can't share tests, you can't compare results. You need a common language. You need a rulebook everyone agrees to play by.
And that rulebook is the ASAM OpenX family of standards. It's like a toolkit, and each tool has a very specific job. OpenDRIVE defines the static world, the roads themselves, the lanes, the signs. OpenSCENARIO scripts all the action, what the cars do, what the pedestrians do. OpenCRG adds super detailed info about the road surface. And OSI is like a universal translator, letting all the different software talk to each other. But here's the easiest way to think about it, and it's a great analogy. OpenDRIVE builds the stage for our digital play, and OpenSCENARIO writes the script that all the actors have to follow. Together, they let anyone in the industry create the exact same scene and get reliable results. Okay, so we've got the method, we've got the standards, we're finally done, right? Time to ship the car? Absolutely not. And this brings us to the most important part, the never-ending safety loop. The key takeaway here is that SOTF isn't a finish line you cross one time. It's a constant, continuous process of learning and getting better. And this is what that loop looks like in action. First, you simulate thousands of those targeted, high-risk scenarios. Then, and this is critical, you compare the results from your simulation against data from real-world drives to make sure your digital world is accurate. You use what you learn to update and improve the AI driver, and then you repeat the whole thing, over and over and over, constantly making that unknown, unsafe area on the map just a little bit smaller. This quote really just says it all, doesn't it? This isn't about passing a test. It is about creating a system that is constantly learning from new data, constantly evolving, and constantly proving its safety through this iterative process. It's a totally different way of thinking about what makes a car safe.
And all of this incredible, complex work leads us to one final, really interesting question to leave you with. We're building this amazing framework to prove that these cars are safe today. But as the AI drivers themselves become smarter and more complex than we can even imagine, how is our own definition of what's safe enough going to have to evolve right along with them?